When considering hypothesis testing, the question at the heart of all this is, how believable is it that the result could have been produced by sampling error if the null hypothesis was true? Consider the following research hypothesis and null hypothesis. Our research hypothesis, what we want to support, eating spinach affects IQ. Our null hypothesis, what we like to reject, is that spinach does not affect IQ. When considering the population distribution of IQ, we know that the mean IQ is 100, that's the average IQ, and that the standard deviation is 16. That means that 68% of the population will have an IQ within one standard deviation of the mean. That's based upon the empirical rule. And that 95% of the population is within two standard deviations of the population mean. So that 95% of the people would have an IQ between 68 and 132. All right, so let's test our hypothesis. We're going to randomly sample someone from the population, have that person eat some spinach, give them an IQ test, and find out whether or not we can reject our null hypothesis. Let's say that the person's IQ turns out to be exactly 100. Well, in that case, the result is consistent with the null hypothesis, and we would retain our null hypothesis. But what if the IQ is 105? Would we reject the null hypothesis then? Well, keep in mind that according to the empirical rule, 95% of any individual randomly sampled from the population will have an IQ between 68 and 132. So an individual having an IQ of 105, not that special. When asking that question, how believable is it that the result could have been produced by sampling error if the null hypothesis were true? We know that if spinach had no impact upon IQ, we would expect 95% of the people to have an IQ between 68 and 132 that we randomly sampled. So 105 is not that unusual. It's very believable that you could get a person randomly selected whose IQ was 105. Now, if the randomly selected person's IQ, who we gave spinach to and later tested, turned out to be 148, that would be noticeable, because then it's much less believable that an IQ of 148 would have occurred just due to random sampling. But here we're just talking about a sample size 1. What if instead we worked with a sample of size 16? With a sample size of 16, our sample mean is going to be a lot closer to the population mean. Anytime you sample 16 people, you're going to get a much better estimator of the population mean than if you just take one person. And so when you look at this distribution of sample means for samples of size 16, the mean will still be 100 because the average of those 16 people randomly sampled is most likely going to match the population mean or be close to it. Any difference would be due to sampling error. The standard error is equal to 4. Based upon the empirical rule, we expect approximately 95% of the population to be within 2 standard errors of the population mean. If you were to get a sample mean that fell outside of this range of 92 to 108, then that would be a sample mean that would be unlikely to be the result of just sampling error. And the probability of a sample mean falling outside of that range of 92 to 108 would be approximately 5%. So in a nutshell, if the probability that your result could have been the outcome of sampling error, if that probability is greater than 5%, we'll go ahead and reject the null hypothesis. That means that that sample mean falls anywhere within this shaded interior region, then we retain the null. However, if the probability is less than or equal to 0.05, then we reject the null hypothesis. For a two-tailed hypothesis z-test, that means that if our resulting z-test is greater than or equal to 1.96, or if the z-test is less than or equal to negative 1.96, we are in that 5% reject zone and we reject the null. And if the z-score is closer to the value of 0, then we'll retain the null. The closer the z-test is to 0, the closer the sample mean is to the population mean, the more believable it is that that the result could have been due to sampling error. The bigger the z-test is for a two-tail hypothesis test, either in the negative direction or the positive direction, the less believable that the result could have been due to sampling error. And we look up our cutoffs using the z-table, and they correspond to a positive 1.96 and a negative 1.96. 2.5% of the distribution of sample means is above a z-score of 1.96, and 2.5% is below a z-score or a z-test of negative 1.96. Okay, so our question, how believable is it that the result could have been produced due to sampling error? We can look at it visually. We can also calculate the z-test. If that z-test value is greater than or equal to 1.96 or less than or equal to negative 1.96, then we know that it's not likely that the result could be due to sampling error, and we reject the null. If the value is closer to 0, we retain it.